nuclear physics and radioactivity. All right. So we're going to be looking at the nucleus of the atom. Again, nucleus is consisted of either a proton, which is a mass of 1.67 approximately times 10 to the minus 27th kilograms, a neutron, which is actually a proton electron together, so it's a little bit bigger, 1.672 times 10 to the minus 27th. Again, this is a charge of 1.6 times 10 to the minus 19th coulombs, and a neutron is 0, and the electron is 9.1 times 10 to the minus 31st kilograms, with a charge of minus 1.6 times 10 to the minus 19th coulombs. So, on that scale then, all right, the nucleus is approximately 10 to the minus 15th centimeters in diameter, or what we call 1 femtometer. And on that same scale, I should say, the atom itself, where the electrons orbit, is approximately, this is 10 to the minus, is approximately 10 to the minus 10th meters, or 0.1 nanometers. Now, this is about 100,000 times bigger than this. So, to get on the same scale, I mean, this is approximately 1 centimeter. If this was 1 centimeter for nucleus, then this would be 100,000 times that, or 1,000 meters. Atom, size of the atom. So about 3,000, 1,000 meters. I'd have to go 1,000 meters high to get the same scale for this. Okay. So that's why most, and this has 99.9% of the mass. So the nucleus, the atom is mostly empty space with this extremely dense material here. This weighs in the order of 1 billion tons per teaspoonful, or per cubic centimeter. This is extremely dense material. This is what a neutron star is made out of, which if you take astronomy, that's another area, but that's the scale, 1 centimeter to 1,000 centimeters, to 1,000 meters. All right, so that gives you the scale of the atom. Now, looking at this, and we'll get into this in more detail, we have the periodic table, all right, which is in the back of the book. And we'll get into the periodic table. We've talked about why the elements are the way they are. But how does it all work? All right, so that's the first part. So, all right, we have the hydrogen, which is 1 proton. We have helium, which is 2 protons plus 2 neutrons. Then the next one is lithium, which is 3 protons plus 3 neutrons. And then, and then beryllium, 4 and 4. And then we go working our way up. We get carbon. All right, so these are the carbon. Now if we look at carbon, carbon has 6 protons, what we call 6C12 plus 6 neutrons. This is standard carbon, which is 99% of carbon or more. And then we have isotopes, all right? So these are both isotopes of the same element. So they're both carbon. This one has 6 protons and plus 8 neutrons. And we'll see this takes up less than like 0.1%. And this is what we call radioactive. Right? So, same chemical. Another one we're going to be talking about is uranium. We'll start going to the other end of the scale. That's 92. And then there's 235, which is 92 protons plus 143 neutrons. This makes up about 1% or less of uranium. And 92, 238 is 92 protons plus 146 neutrons. And this makes up about 99% or so. All right, these are both radioactive. So all of these are radioactive, meaning the sense that they will decay to something else. We'll get into that. Now, if we look at this idea of radioactive decay, there's a chart in the book which shows what we call a number of nucleons. And this is so-called binding energy. And I'm not going to get into the details of that. But first of all, before we talk about this, before we move on so far, this up here, this number up here is the total. So if we have carbon 12, this is the what we call the atomic number. And this is what we call the mass number, which is protons plus neutrons. So this is strictly a number of protons. This is a number of protons plus neutrons. So again, the chemical properties of the element are determined by the number of protons. Right? The isotopes are chemically identical, but they have different properties. And we'll see that, particularly when we talk about fusion and fission in the next chapter, chapter 31. What we have here is, we'll get into this a little bit, but this so-called binding energy curve. So we have hydrogen down here, and we have uranium and other things way up here. And what this means is, and it peaks right at iron, which is 26 protons, peaks right here. Everything less than this can undergo what they call fusion, which are atoms combining, nuclei combining together to make a new element. On this side, you can either do radioactivity, well, the other side can undergo what they call fission. All right? So this is what we go. Everything kind of ends up in that direction. And throughout here, we have different elements that are radioactive, meaning they will eventually break down to something else, some other chemical. Some other element. All right? So these are the ones we're going to focus on. We're going to focus a little bit on carbon for what we call carbonating and uranium for dating of very old rocks. All right. This binding energy graph, which is in chapter 30, will be primarily used for chapter 31. So, what do we have here? Okay, so I'll start with this 238. All right. So we have uranium-238. And what it does, and it was discovered in 1897 by Henry Becquerel. And then in the 1903 or so, by Marie Curie and her husband Pierre Curie, was more work was this. Henry Becquerel discovered radioactivity by exposing enclosed photographic plates, I mean they were wrapped, to a sample of uranium. And what happened is, when he developed the plate afterwards, even though it had been contained, it was exposed. And so it had some sort of radiant like light. Light cannot penetrate. So if you just have light trying to penetrate, say, photographic plate inside an envelope, it won't penetrate and nothing will happen. It's much like a camera. You have the lid or the cover on a camera. You take a picture with the lid cover on, nothing will happen. But if you put the cover, have the cover on, put it next to a piece of uranium, then something will happen. It will get exposed. And it will turn out this is actually X-rays that happen, because X-rays can penetrate solid material. So X-rays can penetrate this and tell you what's inside. Okay? So we talked about X-rays back in chapter 22 on electromagnetic radiation. So Marie Curie and Pierre Curie discovered uranium. Well, they hadn't discovered it, but they also showed that it was radioactive, along with radium and polonium. Okay. And polonium, they named after the country she was from, which is originally Poland. Okay, so what is radioactivity? So radioactivity again, this only deals with the nucleus. The only thing that's happening is the nucleus. This has nothing to do with the chemical properties of it. So if we start uranium, 238, this is 92. What they discovered is it breaks down to thorium, 90, 234, and emitted what they call an alpha particle. So that's the Greek letter alpha, which actually turns out to be a helium nucleus of 2 protons and 2 neutrons. But at the time they weren't aware of that, but they just knew it emitted some particle. And partially, when we talk about lab 13 on radioactivity, alpha particles are particles, so they can actually be stopped fairly easily. We get into radioactivity, that's lab 13. All right, so this is what it broke down to this. Now, we'll get into how long it takes, all right? So that's radioactivity. And now, next type is then, if we take carbon 14, which we said is radioactive, it'll eventually break down to nitrogen 14 plus an electron. So this, and what happens is a neutron converts to a proton plus an electron, all right? Both proton and electron have opposite charge, and it turns out the mass of these is about the same as the mass of the neutron. So you have this is what we call a beta decay. And what happens is the carbon breaks down to nitrogen 14 and emits beta, what they call beta decay, which is beta particle, which is an electron. And then the final one, which is a little more complicated, and we're not really going to do with that much, is if we have some sort of excited atom, it'll break down to a less excited one plus emit a gamma ray. And this is a gamma ray. And this is actually a high energy photon. Right? That's what we call gamma radiation. And this is just like an excited nucleus becomes less excited and emits a gamma radiation. This is common for chemistry, so it's actually a photon, it's not a particle in the normal sense of that. This is a helium nucleus, and this is an electron. So the two we're really going to be focusing are these two. Alpha decay and beta decay. And we're going to kind of neglect it. We'll talk about that in lab 13 because gamma rays are more energetic than X-rays and therefore can penetrate even more material. We have gamma rays coming all the time through the atmosphere. So let's go on from there. Okay. So what we see is if we look at, say, a sample of uranium, right? So number of U-238, and we look at time, or some let's say some radioactive sample. So we have something radioactive. And we have N, let's say we start with 100 atoms, right? And we're going time. And what it means is it breaks down to another thing. This is what we call like a daughter element. So we're not going to get into length of time, but say we start with uranium-238. And we start with 100 of them. After some period of time, it's going to what we call a half-life. It will break down to 50. After a similar amount of time, it will break down to 25. After a similar amount of time, it'll break down to half of that, and so on, and 6, and eventually, and this is what we call exponential decay. Okay, so this is an exponential decay, and this time, this time is what we call the half-life. And how does this act? So this exponential decay is n. We start with n naught, which in this case would be n naught, e to the minus t lambda times t. Where lambda is what we call a decay constant. Okay. Now, so what does this mean? So the way this works is that there's a certain amount of time for it to decay. Now, in an atom, in a sample, I mean, you can have even 1 gram, you can have like 10 to the 23rd atoms, right? A lot of atoms. Now, they're not going to all break down at once. Some are going to go very quickly, some are going to take a long time, very long time. They don't all happen at once, right? So this term of half-life and this decay constant, lambda, so this is the exponential decay given by this expression. And then we can write this in terms of half-life by using the fact that we call this term tau, and we have 1 over lambda is t half-life over 0.693. So what we can do is replace lambda with 0.693 over t half-life. So this will be time in half-lives. So then we can write this expression here. N is n naught e to the minus t times 0.693 over t half-life. So in terms of half-lives, meaning 1, 2, 3, this will get you, so after 1 half-life, so when t equals 1 half-life, when t equals 1 half-life, then n will be n naught times a half. When t is 2, then n will be n naught times half times a half, which is a quarter. And when t equals 3, then n will be n naught times a half times a half times a half. All right? So that's what you have there. And that's what we call by exponential decay. And so we can write then this expression, so in terms of half-lives. And that'll be what we'll do later on, okay? So don't forget the 0.693 in there. All right, so how does this work then? For radioactive materials, then, let's have that expression. So if we have for radioactive materials, all right, where, again, let's do n is n naught e to the minus t, lambda times t is n naught e to the minus t times 0.693 over t half-life. For uranium 238 has a half-life of approximately 4.5 billion years. Meaning, or you start with 100 atoms, 100 of uranium-238, after 4.5 billion years, you will go down to 50. After 4.5 billion. After 9 billion, another 2 half-lives, it'll half of that, so it'll be down to 25. After 13.5 billion years, it will be down to 12.5, and so on. And after 18 billion years, it'll be down to 6 or so. So this is 1 half-life, 2, 3, and 4 half-lives. This is how uranium decays into thorium. So it decays from uranium-238, breaks down to, this is how much uranium is, and the rest of it goes into thorium. So what you would have is thorium be 50, 75, 87, 94. Now thorium doesn't stay that way, but this is theoretically what would happen. Now it doesn't end up that way. There's a so-called decay chain. And I can show this. All right. So if we start with uranium-238, it breaks down to thorium-234, but then notice it goes to the right. And I'll get to this, I'll sketch this a little better. And this is what we call a decay chain. And the way this works is if we have a graph of what we call Z, which is number of protons, and here's A, the mass number, number of protons plus neutrons. So we start with uranium-238, starts at 92. So it's at 92, it will decay down to, I'm going to do this on a much larger scale. This will decay down to thorium 90. Thorium 90, 238. So this comes down to from 92 to 90, and this goes from 238 down to 234. That's what we call an alpha decay. Now what thorium-234 does, it undergoes what they call beta decay. So it actually, that proton there decays to palladium 91, and so this is 91, 234, and then decays again by beta decay to uranium-234, 92. So uranium-238 starts as breaks down to uranium to thorium 90, 234 plus an alpha particle, helium nucleus, at thorium-234 breaks down to Pa-91, 234 plus a beta particle, which is an electron, and then that Pa-91, 234 goes to uranium-234 and 92 plus another beta particle. So this is what we call a decay chain. And it'll keep going and going and going. There's more. If you can do the steps, and then this graph shows that this undergoes more and more and more, right? So I can keep going, and this would eventually go down to thorium at think it's 230. Yep. And then goes to radon, 228, 88. So eventually, the uranium breaks down to thorium, which eventually by beta decay becomes uranium, which then decays to thorium, which then decays to radioactive radon. So radon, 88, 228, is also radioactive. The problem why radon, and this is radon, is so radioactive is that it's known as a noble gas. That's not true. Oh, my mistake. Radon, this is radium. This is radium. Radon is radioactive. Radium eventually breaks down to radon. So this is radium, and this breaks down to radon, Rn 222. I believe. Yep. And this is 226. And this is 86. And this is radon, which is a noble gas. And this is, because it's radioactive, both of these are radioactive. Radon stays as a gas, and if you ingest it, the alpha radiation from radon can be quite hazardous. So we get rid of this. And the only reason I'm showing it is that uranium eventually breaks down to radon. And radon is dangerous because radon 222 breaks down to polonium 218. Plus an alpha particle. And this, if it's inside, alpha particles, not dangerous, unless ingested. Inhaled, I should say. Unless inhaled. So once this gets into your lungs, because radon is a noble gas and doesn't react to anything else, once you inhale it from radon gas from the ground, this can be quite dangerous. We'll talk about that. 31 with biological effects. All right, so let's have what we call half-life as far as that's concerned. The last one here, we talked about uranium-238. And this is for dating old rocks, right? So if you find uranium and the byproducts, you can actually date old rocks because this is older than the age of the Earth. So most of the original uranium from 4 billion years ago is still around. All right, so that's it there. Now let's look at another one last one. And the other example I'll be talking about is with carbon, 14, right? Breaks down to nitrogen and emits a beta particle. All living things have carbon in them, right? 99%, let's say 99.9% of carbon is carbon-12. Roughly and it doesn't have to be exact, about 0.1%. It's probably more than that, but just to be, is carbon-14, and this is radioactive. So the ratio of C12 to C14, just for an example, is about 1,000 to 1. Right? It's not quite that, it's probably more than that, but just as an example. All right, so this has a half-life of 5,760 years. And how can we use that to date things? So anything living, once living, can be dated. Depending on up to about 50,000 years is the absolute maximum. Okay? More or less. So how does this work? Well, since this is a half-life, 5,700 years, and the age of Earth by radioactive dating rocks is about 4 billion years. Right? So in that sense, if we just started with a certain amount of radioactive carbon, it would have long since disappeared, and it would be worthless as a dating because there'd be none left. Because this is almost 1,000 half-lives, and 1,000 half-life, do a half 1,000 times, and you end up with nothing. But it turns out in the atmosphere, right? The atmosphere is 80% nitrogen. Okay? Now, we talked about cosmic rays. Cosmic rays, gamma right there, big particles. Coming into the atmosphere will hit a nitrogen atom and turn that into carbon. So then instead of nitrogen 14, you have carbon 14. Now this doesn't happen very often, but it happens enough that the amount of C14 is more or less constant. Okay. So the amount, as this carbon-14 decays over time, based on the fact that we have a relatively constant shower of what we call cosmic rays, and since the atmosphere has been roughly the same for the last billion years or so, the amount of carbon-14 in the atmosphere is relatively constant. So as you breathe in, inhale, plants take in carbon dioxide, so photosynthesis involves carbon dioxide, which then by photosynthesis produces oxygen, and we eat material, we eat things, they have about the same ratio. So in living things, back to here, the ratio is roughly 1,001 or so, whatever it is, right? The ratio is not important. The actual number is not important. So let's take 1,001, right? Is 1,000. All right, so you eat, you're strong, you eat mussels, and then suddenly you die. And let's say you die out in the desert and are forgotten. And then let's say 5,060 years later, somebody discovers what's left of you and discovers, takes some of that. They can then find the ratio of that. Oh, this should be the other way around. Okay. And they notice that the ratio gives C12 to C14 roughly is now 2001, which means that the carbon, this is half the amount we had before. If we discovered it 11,520 years later, then the ratio would be C12 over C14 would be 4,001. And what we see here then is that in something that is dead, the carbon in there is fixed. Right? It's not nothing more is going to be added. So any carbon 14 is going to decay to nitrogen, which will just be lost. And over time, that's how we can find the age of that object. And so we'll then use half-life by looking at the ratio. So if you have half the amount of carbon 14 we had before, so if we start with 100 molecules at C14, 100 after one half-life, it'll be 50. After two half-lives, it'll be 25, and so on. And so N will be N naught e to the minus T times 0.693 over T half-life. And so based on this example, using this again, something was living at one time, it's a complicated process doing this, you can determine how old an once living thing was. So plants, people, paper, I mean, it's been dated to date a number of things, like Egyptian papyrus, the Shroud of Turin, which is thought to be the burial cloth of Jesus. However, carbon dating puts it to about 1390 AD. And so that's what we call radioactive dating as far as that's concerned. So that is chapter 30. Okay.